Hello friends, uh, in this video we are going to talk a bit about certain concepts and certain questions of IB physics, and today first we will begin our discussion with problems on mechanics. The mechanics, as I've seen during teaching, that it is one of the most challenging sections that the students um, of IB experience. But it's mainly, I think it is because of the way mechanics is understood. So obviously, if the concepts are in place and if we are able to understand the underlying principles, mechanics definitely can be one of the most rewarding sections of IB physics. So today we'll try to go through certain concepts and certain problems of mechanics. Let's see how we whether we can understand them properly or not. Now, first of all, our first problem will be focused on our concept of inclined plane, and there is a bit of knowledge of vector resolution that is required in order to understand this problem. So before going into that, before going into the problem itself, I'll try to discuss about the basic concepts of inclined plane that all of you need to be okay with. So first of all, over here we have drawn a block which is sliding along an inclined plane, which is inclined at an angle theta, let's say. So you can see that the weight of the block is certainly acting downwards, and you can see it over here. The force which is weight, has been resolved into two components. One along the plane, which is W sine theta, and the other perpendicular to the plane, which is W cos theta. Now, obviously, this resolution is to be understood first. So I'm going to go over or go through resolution as well a bit while going through this problem. Now, resolution is property of vector where you can think of one individual vector to be composed of multiple components. So the advantage of this particular process of resolution, which is rectangular resolution, is that we can consider the two components separately. And I'll try to explain why it is so. It is one of the most important concepts of mechanics that is used in multiple situations, and we'll try to understand how it is made possible. So let's say over here we have a vector, and let's say I give it a particular name. So let's say I give it the name of a vector. Okay, so this is the vector that I'm talking of, the intermediate vector that you can see. Um, so over here, the vector A, you can think of not being existing as just A, but being made up of two components. So over here, I've drawn these two components for you. Now, let's say that this original vector A is being broken down into its components. So you can understand that, let's say if this angle between the vector and the horizontal direction is something like this, theta, then certainly if I use the triangle rule of vector addition or parallelogram rule, any one would suffice because it is essentially the comfort level of the students that matter. Some people are comfortable with triangle rule, some are comfortable with parallelogram rule. Whatever it is that you are comfortable with, you can use. So what happens is that over here we can think of the vector A to be composed of these two vectors. So let's say if I draw the two vectors properly now. Yes. So I can think of these two vectors, which is making vector A. These are the components of the vectors. So over here, the two components being a cos theta and the other one being a sine theta make up the vector A. Now, how is it that we know that? How is it that we can prove that it is indeed these two vectors, a cos theta and a sine theta in this particular direction, which will make up this vector A? It's very simple to prove actually. Uh, if you use Pythagoras theorem, you can understand that the hypotenuse, which is represented by vector A, is having the magnitude of A. Also, how is it that we know that it is in these two directions only that we'll have these two components? It's actually not known. You can have multiple components in multiple directions, but we have chosen these two directions for the reason that you can understand that the component along, let's say, the horizontal direction, I've taken that to be a cos theta. So let's say I write that the horizontal component or the x component to be a cos theta. Now, obviously, if the the value of theta changes, I hope you can understand what happens. If the value of theta changes, you can understand that this ax, the component of the vector along x-axis, that also gets changed to the extent that if theta becomes pi by 2 or 90 degree, obviously we can understand that this ax becomes 0. In such a situation, you can understand that if instead of this vector being in this direction, if let's say I consider the same vector and I'm translating it, and let's say if I am rotating it like this, okay, like this, so I am keeping the magnitude constant, but you can understand that its components would change. So in this direction, you can understand that the x component would be something like this, and I hope you can understand that the y component would be something like this. So you can see that it's the y component that has changed, the vertical component that has increased quite a bit, and the horizontal component has reduced quite a bit. The reason is we have changed theta. So as we change theta, the magnitude of one of the components gets changed, and eventually it vanishes at 90 degree when the value of theta is 90 degree. So what we understand is a very interesting fact that you can have a component at any angle, but not at an angle at right angles to the direction of a vector. So what we mean by that is that a vector cannot have any component perpendicular to itself. So if you think of these two components, a sine theta and a cos theta, these are components which are perpendicular to each other, and hence they themselves cannot have components along the other direction. Now, the physical meaning of a vector having a component in a direction is that it would have an influence in that direction. So instead of vector A, if I consider a force, let's say, it will have its effect or acceleration, or let's say because of acceleration, displacement of an object, that is possible in both the x and the y axis according to this diagram, according to this direction of vector A. But we can understand that if this vector A becomes vertical, it will have no effect along the horizontal direction. So no acceleration or no velocity is possible for any object. If let's say a force acts along the vertical direction, there would be no velocity or displacement of the object along the horizontal direction. So that is the most important conclusion that we can arrive at from perpendicular components, that they do not have an effect on each other. Hence, a cos theta and a sine theta, they can be taken separately. They are said to be treated independently. The same thing I hope you can understand here. So this was about vector resolution, rather perpendicular resolution of vector. Uh, so in this case, what we talked about is vector resolution. Now this is a particular case of vector resolution called rectangular resolution that we talked about, meaning that over here the angle between the components was 90 degrees. Right. So if we apply that in the case of our original problem of our inclined plane, you can understand that the same vector W instead of a vector has been resolved into the two components, W cos theta and W sin theta. And this is based on our application that the angle present here is also theta. So I think you can try to do it, everybody, if you just give it a try with a bit of geometry, with a bit of just a bit of application of that, and you'll be able to understand that the same angle of inclination theta is existing at this point. So if it's the same theta, it's like this theta. So you can understand that the angle that is existing is or rather the vector that the components that are existing are W cos theta and W sin theta. In fact, based the value of theta incorrectly, it is this theta that I'm talking about. Right. Just make a note of that. Just use a bit of geometry and you'll be able to prove it yourself. So I hope it is clear to us that the two forces that are acting on the block as it's trying to slide down is W sin theta and W cos theta. Of course, if the block is not sliding, what's stopping it? What's stopping it? Yes, you guessed it right. It's absolutely friction. So certainly there is going to be another force of friction acting in the opposite direction, in the upward direction, if it's not sliding. But for the moment, we'll not consider that. We can consider that in our forthcoming videos and try to make another one where we include friction. For the moment, it's a frictionless plane, so obviously these two forces are acting. Other than that, there is also another force that's acting that I have not considered. That is the normal reaction force given from the plane on the block. So if I have to label it, let's say I give it the name of N, the normal reaction force. So this force is acting, which is balancing W cos theta, which is why the block is not moving upward. So having established the basic concepts that are needed while solving problems on inclined plane, let's try to move over to our problem itself. This is not an extremely new problem or an original problem. I do not claim that. It's just a problem taken from an IB paper. So if you just go through this problem, you have a block again that's sliding along an inclined plane, and it is we have been asked that there is a case of friction in this case that's involved. But trust me, for doing this problem, we will not need any application of the concepts of friction, or for that matter, mu, the coefficient of friction. We'll discuss that in our later videos. So the question is about what's the total energy that's transferred when the object travels this distance. Obviously, if there's a question of thermal energy that has been generated, it's certainly because of friction. So over here, the object is certainly experiencing change of gravitational potential energy as it's sliding down, which means that this energy that it is getting by losing GP, or gravitational potential energy, should be available in the form of change of kinetic energy. But look into this, everybody. We have also got to consider the work done against friction or thermal energy. So let's try to see what the work done would be. Now, if you take a look into the problem, it says that the object is moving with constant speed, which means that on the object there cannot be any net force. So if you consider the W sin theta that I considered over here, if on the object there is a frictional force that's acting. So let's say it would obviously acting in the opposite direction like this, and if the object is moving with constant speed, these two forces, W sin theta and this friction, would balance. So in this case, friction would be equal to W sin theta. So just take a moment over here, everybody. You can I hope you can understand that over here friction would be W sin theta and nothing else. So if I use that expression of friction, that it is W sine theta, then you can understand that the work done W would be that frictional force times the displacement that it is suffering. So we can understand that the work done in this case, or the work done against friction in this case, would be this. However, if the work done is this, but the value of force F is just W sine theta. I hope you understand that, because we have established that friction and of course our the component of weight along the inclined plane, both of them are equal. We have established that because it is moving with constant velocity. So what we can write is something like this. This work done should be something like this. Take a look. I've just written, instead of the force, I've written mg sine theta, w sine theta, because over here the object is moving with constant speed. So the frictional force is w sine theta. That's what I've used. So that's the value of work done against friction. Now, if I try to find that out, if I try to find what angle, if I try to find it in terms of the angle, just take a look. This angle is our theta, let's say. This angle. I hope you can see it. So this angle is theta. So is this angle. Take a look. This angle as well. So you can understand that if I try to find out sine theta, and we know that this part is this height is h. That is what we know. So this height is, let's say, h. So you can understand that if from this small triangle that you can see, if I find out sine theta, I hope you can understand that it would give us h upon x. Just do it with the help of trigonometry, of the basic trigonometry, and I'm sure you'll get it. So if sine theta is h upon x, uh, you can understand that what would be x sine theta. So let me just try to write it over here. That what we have got is that sine theta, that is the ratio of h and x. If that is the case, yes, if that is the case, then you can understand h sine theta would be just h. So if x sine theta is just h, then you can understand what the work done would be. It's just going to be, I hope you have got it, you have guessed it right. Now let's check it whether you have guessed it right or not. Yes. So it's just going to be mgh. But this is definitely a very, very familiar expression for most of you. So here the expression means that the change in GP, which is actually mgh, that is also equal to the work done against friction, or thermal energy. Normally, this is an interesting point of consideration. That normally, if there is a change of GP, or gravitational potential energy, there's normally a change of kinetic energy. But can you guess why it's not here? Why it is not here? The reason it is not here is because the object is moving with constant speed. So there is no change of kinetic energy. The kinetic energy is staying constant. So the only way the change of GPE, or gravitational potential energy, can be converted is by doing friction. So the object is losing gravitational potential energy, and that entire energy that is made available to it is not converted into kinetic energy, but into doing work against friction, in overcoming friction. So that's how we can understand in this simple problem, principle of conservation of energy also holds good. And actually, each of the problems of IB is a combination of multiple problems, if you are able to think about it. So that's actually one of the most elegant features of IB problems, that it makes you think. So if you're prepared properly, I'm sure you'll be able to do these problems comfortably. Now moving on to the next problem. Over here, it is something like this, that you have there are two forces acting on an object, and one is a constant force and the other is a varying force. What there has been some options regarding the nature of acceleration that would be experienced, or the nature of velocity. So if you take a look, everybody, into this problem, the moment you read this problem, what should come to your mind is the concept of terminal velocity. Think about it. In terminal velocity, when an object is moving down, it is also experiencing a varying force, the one due to air resistance, which varies with velocity, and there is, of course, the weight of the object that's acting down. So in this problem, you have just the case of terminal velocity for an object moving with air resistance reframed in a particular manner. So that's the beauty of IB problems. Take a look. You have those problems reframed, they can be reframed in this manner. So obviously, then the question becomes very easy, that you over here you have to have option C to be correct. You know how the velocity time graph looks like for an object moving with terminal velocity. It initially increases, and then you have the air resistance catching up with the weight, and then eventually there is no acceleration, so the velocity reaches a maximum value. So it is this option C that we are talking about. One important uh, conclusion, or one important consideration from this is the case that if you have ever experienced or enjoyed rain, it is because of this air resistance. So think of it, the raindrops as they fall through the atmosphere and into our head, let's say, if we're standing out, they are hitting us with terminal velocity, everybody. And imagine what would have happened if it were not so. If they were hitting us with the acceleration, my God, they would have been like bullets. So it's a great thing that we can enjoy the rain, and it is because of this concept of terminal velocity being applicable to them. Otherwise, you can do simple math, and you can just think about it, that terminal velocity is what is saving us. So long live terminal velocity. I think that's what we have to say. Okay, so I think that's what we have for this short video. I just thought of discussing some concepts and certain problems with you. Although this is just two problems, but I'm sure it's going to be necessary for the preparation of IB physics wherever you are. And I teach both online and offline, so I thought of sharing something with all of you. If you have any further queries, you have my email ID available, and you can definitely get back to me on more. Of course, if you like this video and you want any specific question to be answered, please get back to me via your comments. Thank you, everybody. Have a nice day. God bless you.